Hello and welcome to another Stephen Mendes video. In this video, we are going to show you how to draw diagrams for mathematical equations. I once had a student fail repeatedly in my first year course, and he quibbled with me over the diagrams. And he said, "Sir, my diagrams are perfectly fine. All the lines are nice and neat, and the angles are right angles, and it's perfectly drawn." And I said, Sir, an architectural diagram is not the same as a diagram that represents a mathematical model. The lines have meaning, and we really don't care whether they're straight, at right angles, or any other angles, as long as we can follow the logic of the maths. So here we look at scaling, summing, and time delay. So let us start with the summing. The mathematical operation of summing is represented. Here is why we're adding 5 to 6 and subtracting 3 to reach 8. Clearly, the summing block, represented by a circle with a plus sign on it, can have any number of inputs, but must only have one output. And the output is all the inputs added together. So there on the right, we see how our mathematical expression is represented with a summing block. The circle with the plus sign in it represents the operation on the left. Now let's take a look at the the time delay. First, we look at the time delay. Now, each of those blocks marked TS delays what is on the left side for a specific amount of time, the same amount of time. Basically, TS is the sample period. So it gets a exact time delay mathematically and digitally, so that what comes out on the right is just slightly displaced from what went in on the left. So clearly we still have to add them back, and we have xn plus xn minus 1, since it's been delayed in time, plus xn minus 2, and we have delayed that twice, which is why it's drawn as shown. So the two time delays are cumulative, and we have the xn minus 2, and then the summing block puts the delayed samples, adds the delayed samples to the original sample, and out comes our y of n. So now we take a look at the scaling. All we have to do to add some scaling is to adjust the amplitude of the delayed signals. So the signals are flowing in the direction through the diagram, as you can see, and they are coming through the scaling block that merely adjusts their amplitude or level, so that we can have the same expression, but now we have regulated the quantity of the delayed signals, which we are recombining in the summer. Now let's look at a student's example so that we may see the difference. Can you see that what is drawn here has a different output to that? Follow where the xn goes. The xn goes through one delay period and immediately becomes the yn. So observe that the output is actually yn equal to xn minus 1. Now we have the xn minus 1 being subjected to scaling and delay. So that gives rise to minus 2.5 xn minus 1 and minus 0.5 xn minus 2. So we see that the block marked yn minus 1 is actually xn minus 2. That's what that is actually is delaying it. But if yn is equal to xn minus 1, yn minus 1 must equal to xn minus 2. And clearly the summing block at the bottom of the diagram is going nowhere. There is no output going to it. Now, we have to make a point that you cannot combine two signals without a summer. In the same manner that you cannot connect two gates, two gate outputs. If one gate tries to go high and the other gate tries to go low, what do we have? We have a short circuit in the logic. So if we have two outputs and one can go high and one can go low, then clearly we are going to have to sum them before we can get a valid output. So you cannot have what is drawn there. Although you can have numerous pick-off points with the arrows picking off, it would be quite okay, for example, to draw this. This is a pick-off. We're taking the signal and we're sending it to two places. But what I'm telling you is we cannot combine two signals without some sort of device to mix them. So we must have the summing block between the two incoming signals that we are hoping to output. So therefore that we can see that mathematical summing is the same as mixing of signals together, whether we're talking about audio or radio frequency signals. We are mixing them together, and the act of mixing music is actually summing. We are algebraically combining the signals. It is the summing that separates the input from the output, or the X from the Y. Now, going back to the student's diagram, even if we were to do that, we still have not got the correct expression. Can you see why? Can you see why? Because what we have actually drawn there is that. Check and make sure that you agree with me that our yn now becomes xn minus 2.5 xn minus 1 plus 0.5 xn minus 2. But what we actually want is that. We want yn is equal to xn minus 2 xn minus 1 plus 0.5 yn minus 1. So clearly what we must have is the separation between the x and y, which the summing block provides. The y side is on the output and the x side is on the input. So all we have to do now is to add the scaling, and we have combined x's with y's. And this is referred to as the recursive element or term. Remember that recursion means that the output is fed back to the input. It's a form of feedback. So our yn, our previous yns are delayed and fed back into the mix. So we have a feedback system going instead of a feed forward when we have the arrows going back instead of going forward. Thanks for watching this Stephen Mendes video, and please give us a thumbs up, like us, and subscribe to our channel for more exciting videos. And for those waiting on the music videos, those are coming too. Thanks for watching, and see you in the next video.